Hello, everyone. Thank you for joining this Climate Program Office webinar on inland flooding and a changing climate, the case of the 2019 Mississippi-Missouri Basin. This is the first of two webinars exploring relevant climate research in Earth system science and modeling, which will be the focus of today, as well as societal interactions, which we'll explore on October 2nd. Stay tuned for email about that. We have a series of 15-minute talks, and we will be taking one or two questions from the audience via the questions panel on the right-hand side of your control panel for GoToMeeting. So familiarize yourself with that. Our five speakers, I'll introduce them as we go through the presentation. But as you can see, we're going to be covering observations and modeling. And we will be getting, therefore, a very broad perspective about the ways that climate scientists are looking at this event. There is a question and answer panel on the right, and this session is being recorded. We will also record your questions, so if we don't get to your question today, there's a chance we'll reach back out to the list to provide supporting material or answers. So please do feel free to use that question panel. Our first speaker is Sarah Kapnick from the River Forecast Center, the North Central River Forecast Center, with an overview of the 2019 Mississippi and Missouri Basin's flooding. And without further ado, I will pass control to Sarah.
No.
Sorry.
I think it's actually me, Corey.
Sorry, Corey. All right, so
Okay.
we had a last minute I should say to everybody, this is Ned Garner, and all mistakes that are being made are mine. I'm with the Climate Program Office, and we had a last minute change in the presenters, and because our speakers is on duty, Corey stepped up and generously offered to make the presentation on behalf of the River Forecast Center, and hence that mistake. So I apologize, and thank you very much for being here today, Corey.
Yeah, no problem, Ned, and sorry about that. That was my fault. I had some travel this week, and due to the recent flooding, that was canceled, so then I was able to make this presentation. So can everyone see my screen here?
Yes, your screen is visible.
All right,
great.
So as everybody knows, that we had a lot of flooding during this spring in both the Mississippi and the Missouri River basins. And at the end, I'll give 10 points to whoever can identify what this location is. So I'm going to give a brief overview of kind of the lead up to the conditions of the flood and some of the records that were broken, and finish up with a little bit of kind of what we're seeing for this next winter and spring. So we always talk about the ingredients to catastrophic spring. So there's 5 different things that can lead to spring flooding, and we almost have to have all of these 5 ingredients to have massive or high flows, and even not even record flows, but at least flooding. So we have to have a high soil moisture, and that's usually in the fall time. We have to have frozen ground, and then we also have, obviously, you need a lot of snow or water within that snowpack. And then the last 2 ingredients are kind of dependent on the spring and how that turns out. Usually a rapid melt is onset by either rainfall and or higher temperatures, and then also spring rain. When you throw that in, you can get an additional rapid melt. So some of the lead up to the conditions of the 2019 winter, to go over this recipe to check off what we have. We had a very wet fall. As you can see with the area circled there, and then both the Mississippi and the Missouri basins, we had upwards of 40 to 120 millimeters of water, very much above normal for the winter time frame. So that really set the stage for the flooding that we had. And then if we also look at the stream flows as well, this is just a USGS map of the average stream flows during that time in the area that's circled there, mostly in the upper Mississippi, but you can see kind of a swath through Wisconsin, southern Minnesota, and Ohio, and a little bit of Nebraska and Kansas there. You can see that we had very high flows, higher than a greater than a 90% of average. So again, having a high stream flow going into the winter really set that stage. And then looking at the second ingredient in the recipe is cold temperatures or frozen ground. As we entered the winter, the fall was kind of near normal, and it wasn't until the end of January. As you see, we set some, in Chicago, you can see we set a record there on the end of January on the 31st of minus 31 degrees Fahrenheit. And you can see that kind of the lead up to that 31st, the 26th through the 31st led to very low temperatures. And we didn't have a whole lot of snowpack. And so when we don't have that snowpack and you freeze that ground, then that frost depth goes really deep. And so looking at that frozen ground and mentioning the frost depths, this is a graphic as of early March. You can see that generally the frost depths throughout the area were about 1 foot to 2 feet deep, and mainly due to 2 reasons. One was the cold temperatures, as I mentioned, and the other one was because we really didn't have a snowpack at that point. And so when we received those cold temperatures, that snow was not there to insulate the soil, so that those frost depths got really deep there. And then looking at the precipitation, or the snow water equivalent, that's the primary driver to our spring floods. And as you can see, both the Mississippi and the Missouri basins, well over 125% of the average or the mean from 1981 to 2010. So you can really see that we had a high snowpack in the area. And then also in conjunction with that precipitation is last winter was the wettest since 1895. And you can kind of see across the CONUS area that much of the area was above average. And a lot of the record wettest areas were in the upper Mississippi area, and in the east of the Mississippi as well, in the kind of the southern states there. So, but across the board, very, very wet conditions over the winter time frame. And then in Minnesota, they do a very good job tracking the snow depth. And again, this is not the snow water equivalent, this is just the depth, but it kind of lends to how much snowpack there was. And over half of the state was in the 99th percentile for the snow depth, which was pretty impressive. And so you can see some of the areas were, a little bit less, but throughout the whole area, we had a very deep snow in end of February timeframe. And then so looking at the climatic outlook of what we had in the spring and what we were looking at, so we had all those conditions, the high soil moisture, the frozen ground, the high snow water equivalent, and the climatic outlook looking at the precipitation and the temperature looked a little wet. You can see from the upper graph there, this is the April, month of April climatic outlook as we're looking at this back in the end of March 21st. And it was showing that, most of the area was about equal chances of, above or below, but there was much of the Missouri Basin that had a greater than 33% chance of having above normal precipitation. And then looking at the lower right graphic with the temperature forecast for the same time frame, much of the area was kind of just a below normal. So at that point, we were really, as far as the ingredients that we did have the soil moisture, we had the frozen ground and the high snow, but we didn't know at that point, how is the spring going to land? Were we going to get rain? And were we going to get rapid melt? And at that point in time, we were unsure. So at that, in that mix of that time frame, we generally put out, every year, we put out a spring flood outlook. And this is the national outlook graphic that was put out on March 21st. And you know, for those that are in the know, we generally have 3 flood categories with the National Weather Service. We have major, moderate, and minor. And so the major is indicated in that purplish color. And at that point in time, due to the wet fall, the deep frost depths, and the high snow water equivalent, we generally had an outlook there, as you can see, of we had an idea that we would see some major flooding along the Mississippi, along the Missouri, and then that northern portion up there is the Red River of the North, which splits the North Dakota and the state of Minnesota there too. So based on those conditions, we knew we were going to have high flows. At least we didn't know if they would be record, and we didn't know at the point on how that snow would melt off, if it would be all of a sudden like a worst case scenario where you have record flows, or if you'd get that you know, that melt out a little bit of a day during the day, and you'd get some like warmer temperatures, then cool down, so you'd kind of get that ideal snow melt. So at the end of March, at least in the upper Mississippi, again, we had a heavy snow cover, and you can see here that you know, the inches of snow water equivalent range from about 3 to 10 inches across the northern area, and even into the Red River of the North as well, in the north of Fargo area. And then, so generally, long story short, at least in the upper Mississippi, we really had a favorable melt and a thaw condition through at least March, maybe mid-March through early April timeframe. And this kind of indicates, these 2 graphics indicate what really happened. So on the graphic on the left is basically the percent of mean for the annual precipitation. And that's really dry. You see a lot of yellows and oranges and reds there. So generally we had a below a 75% average from about March 15th to about early April. So that was a really dry time frame, even though that, you know, we had the very wet fall and the wet early spring. The meat of the spring was definitely a little bit drier, and that was for sure a help for us. And then on the right graphic, looking at the temperature, you know, and as I talked about the ingredients to flooding, temperature plays a major role. Most of the temperatures, as you can see, were kind of in that middle band, that goldish color, which is about normal. The vertical blue bars are what the observed temperature range was, and you can see that most of the temperatures were within that normal range. Some of them were above normal, you know, and 1 or 2 days were below normal, but generally we had normal to above normal temperatures, and that translates to an ideal melt. When we hold on to really cold temperatures throughout the spring, generally and historically speaking, that's when we get into trouble and it melts off very rapidly. But if we can have moderate temperatures in the early springtime, then that really helps with that melt, to basically melt gradually and get that get the snow to enter into the rivers in a gradual process there. Kind of segueing into, and that was the upper Mississippi, segueing into the Missouri Basin. In March, there was the big bomb cyclone that led to record flooding due to heavy rain from that precipitation event, and that led to rapidly melting snow and triggering ice jams, because we had those really cold temperatures and there's ice jams all over, and with that melting created that flooding. So overall, about 42 locations set new record levels, and most of those locations, as you can see from the graphic on the left, were in the Missouri Basin there, across the, you know, in the Missouri and the Kansas area. But there is, you know, across the Missouri River, south of Omaha, Pratt's Mouth, Nebraska, Brownville, and Rulo, those each topped their previous record from June 2011. So 2011 was a big year across the board, and mostly within the Missouri Basin. And then also the Missouri River at St. Joseph and Waverly exceeded the 1993 flood. Most people were talking about 1993 when we were in the midst of you know, our melting, and comparing 93 to what we were seeing. So in the Missouri Basin, there was a major rain on snow event March 12th through the 14th. And with that, the SWE, or the snow water equivalent, as of March 11th, this is, the graphic on the left is overlaid by the rain on snow event starting on the 12th and concluding on the 14th. And then add to that the deeply frozen ground with perhaps about 85% runoff to the precip melt to ratio. Basically, we had about a 2-inch rain fall over about a 2 to 4 inches of snow water equivalent. So a 2-inch rainstorm becomes a 5-inch rainstorm with the frozen ground and basically no infiltration into the soil. So it may be like a 7 to 8-inch rainstorm. And so when you get those totals, that is catastrophic. You're getting all that rain going into the Missouri Basin. You can see a couple pictures on the right of photos that a dam that failed, and also additional flooding as well. So everyone wants to see pictures, and so I have here a few scenes of devastation. Just a few photos of this is on the Missouri Basin here, the Pine Ridge Reservation in March 2019. You've got the Goose Creek in Sheridan, Wyoming, where floodwaters reached pedestrian bridges there and closed them off. And then, of course, the Missouri River. Here's kind of a decent picture with showing the extent of the flooding and the impacts to the agricultural area in June of this year. And then the last photo is kind of an overview or a satellite view of what it looked like the Missouri River on the 21st of March last year, to kind of compare what a March river looks like to what we had this year on the 16th of March. And you can see it's a very big contrast with the amount of water along the Platte River and into the Missouri River there. So you can see, and even the Nishna-Nabatna River as well, just very much swelled. So it's interesting to see these satellite graphics. This graphic here is a little bit busy, but I'll try to explain this. This is our flooding at Davenport, Iowa, to show the duration and intensity of the flood. Again, 1993 at this, generally in the upper Mississippi, was the record flood. And at this station, the record was 22.63 feet. And this 2019 was a new record of 22.70 feet. Not a big record breaker, but indeed a little bit higher, and that was on May 2nd. There's also a couple other records. There's a new number 10 on the record, that was on April 8th, and then also a new number 6 on June 1st with the heights you can see there. The previous to, after 1993, 97 was an analog year. It used to be number 8. It's not anymore. And that record at 97 was shy under 20 feet at 19.66. But to show our forecasting, and that's what we do at the North Central River Forecast Centers, we put out the daily forecast, and we were very busy, as you can see from this graphic. So we went at 96 consecutive days of having issuing flood forecasts, 94 consecutive days of having moderate flooding, and then 51 consecutive days of having forecasts above major. And this graphic, it looks, you're kind of wondering what those different things are. Those are each day's forecast. And as you can see, during that time frame from about mid-March, from about 15th March to mid-June time frame, you can see that this station was in moderate flood. This is the Rock Island station in Davenport. So you can see that we were very busy during that time frame. And then kind of looking at the Missouri Basin, here's the locations experiencing major flood. All those purple dots, generally purple, corresponds to our major flood. So you can see all those dots everywhere along, even in through Montana, North and South Dakota, Nebraska and Iowa, and into Missouri and Kansas there. Tons of major flooding there. And this graphic here came from our National Water Center. They sent out a tweet saying that when was this? May 31st, 68 total river gauges were at least in the preliminary records at that time frame, still yet to be confirmed by the U.S. Geological Survey. But you can see through the map there, most of them in the Missouri Basin and a few in the upper Mississippi Basin there. So what does it look like? You know, what was the soil moisture with Missouri Basin last year compared to this year? You can see that in 2018, you know, not very wet at all across the CONUS area, but you look at the graphic on the right, and a lot of much above average to even record wetness in the August 28 to July 2019 time frame. So again, just showing that soil moisture in the Missouri Basin. And then, so what does the fall precipitation outlook look like? Well, last year when we went into flood, there's the EC, or the equal chances of normal precipitation for the September, October, November. That's the SON with that arrow there on the left. So September, October, November, the outlook was for fairly just normal conditions precipitation-wise. What are we seeing now for the same time frame? Well, above precipitation is forecast, at least in the Central Plains area, and even bleeding over into the north, the Minnesota and the Wisconsin and the Iowa area there. And even you've got above normal precipitation pattern predicted for the Missouri Basin. So we'll have to see what, as we progress through the winter, how things change or keep the same. So my last slide here, and I'll open it up to questions, is 2020. So what are we looking at? You know, no one can really say what 2020 will bring hydrologically to either the Missouri or the Mississippi basins. You really can't predict these bomb cyclones or these extremes, the cold winter, the amounts of snow. Those are yet to be seen. We can compare today's conditions, what we're seeing now, to what we saw last year as well. We're definitely wetter. We've had this far, it's been colder than normal, and it's definitely been wetter. We've been receiving a lot of wet a lot of precipitation, so we're leading into this fall with, you know, very high stream flows and very wet conditions. So it's kind of lending towards or setting the stage to potentially another flood next spring, but we'll have to see. So we can't remember, you know, 2011, that was followed by a 2012. So we definitely can have two big water years in a row. So to kind of look at, you know, the probabilistic river outlooks, NCRFC and Missouri Basin RFC will start putting their outlooks in December, and then our RFC, the North Central, will start around January. And again, these are very crude. They're 90-day outlooks of what we're seeing and what we have in the model, and with the conditions of what's happening at the time. So looking out 90 days. So that's when we can start kind of looking at what 2020 will bring. And with that, I'll open it up to questions.
Thanks, Corey. And I don't think we have time for a question, but I will point out Terry Simmons did suggest that picture at the beginning was Davenport, Iowa, after barriers were breached. Is that right?
That is correct. So he's the winner chicken
right.
dinner on that.
Terry wins the 10 points. And thank you so much for that overview. And I think everyone at NOAA agrees we value the role that the Weather Service plays in providing accurate forecasts to protect people. Andy Hull is our next speaker. He's a meteorologist at the NOAA Earth System Research Laboratory, the Physical Sciences Division, who focuses on researching the physics and predictability of regional weather and climate. We're running a little behind, so without further ado, Andy, take it away.
Well, thank you, and I'll try to keep us on time. I'll do the best that I can. Good afternoon to those in the Eastern Time Zone, and good morning to those west of the Central Time Zone. What I'll do today is I'll share some results from a diagnosis of the causes and predictability of America's wettest winter. And winter here is December, January, and February of 2018-2019. This is based on a paper in preparation by the same name. And this ties in with the webinar in that wet conditions during winter helped to set the stage for the inland flooding during spring of 2019. So based on NCEI data, December 2018 to February of 2019 was the wettest on record over the United States. The upper left-hand panel is the precipitation anomaly over the United States in millimeters per day. The upper right-hand panel is the percentile ranks to give this an idea of how the precipitation distribution varied in space and also varied in time for historically for 2018-19. And the bottom panel here is just the time series of area averaged U.S. precipitation. And what I mean by that is the contiguous United States, so none of the outlying states and territories. What's really remarkable here is that top tercile precipitation east of the Rockies in much of the western United States. I mean, a map like this is pretty remarkable in the sense that the only place that we actually saw below average conditions were over the front range of the Rockies and even in the Pacific Northwest. And over the areas in which we saw the flooding, we saw top decile, and even it was just top decile, top 1% over Missouri, Mississippi, Ohio, and Tennessee River valleys. What's noteworthy here in the bottom panel is that we're not seeing a discernible trend or change in the variability of area average U.S. precipitation. From this time series right here, you don't see a trend. There's nothing significant about it. And what I've also overlaid here are the 30-year and 10-year running standard deviations of U.S. precipitation, really to highlight that we haven't seen any discernible changes in the variability. We see decadal variability here in the 10-year standard deviation windows, and the 30-year windows tend to be pretty flat. There's a little bit of variation in there, but not by very much. This picture was shown previously, and it really shows that the winter wetness that we experienced during December, January, February of 2018-19 was helped to inform the springtime flooding. And the wetness here that was observed in the top 1% top decile precipitation really coincided with these areas in which there was an expectation for major flooding over those river basins. Now, this winter was interesting for a number of different reasons, but it also happened in the midst of an El Nino event. And though many features of this El Nino event deviated from what the historical composite would show us. So just going over this, in sea surface temperature space, what we saw here was a pretty moderate, pretty weak, not really a substantial El Nino event, with an SST anomaly expression here that's really mostly over the central Pacific Ocean. Over the eastern Pacific, we saw warmer than average temperatures, but certainly not to the degree that we would see during a strong El Nino event like 2015, 16, 82, 83, and 97, 98. And in terms of global precipitation, which is sort of a metric that one would use in order to understand what is going on in terms of the teleconnections that are coming from the tropics, this precipitation pattern is rather different than what we had seen in historical El Nino events. We had above average precipitation over the central and western Pacific, western tropical Pacific Ocean, but really nothing that's coherent here that projects onto the strong El Nino composite that I'll show next. In terms of geopotential heights, this pattern right here is not indicative of a historical El Nino from that perspective. And as a result, we see quite a bit of difference. It's more like a wave pattern going through the atmosphere as opposed to what we would tend to see coming from an El Nino event. Now, how does this deviate from the historical El Nino? Well, the sea surface temperature anomaly pattern is rather different. The precipitation pattern is rather different as well. Coherent pattern above average precipitation over the tropics, over the western Pacific and the maritime continent, below average precipitation, and certainly in terms of geopotential heights, we didn't see this wave train emanating from the tropics that we tend to see during El Nino events that we saw in 2018 and 2019. Now, one thing to touch on before we move on is that forecasts didn't anticipate the 18-19 wetness. On the right here is the forecast for December, January, February that was made in October. And on the left here is the precipitation percentile that I showed previously. The forecast didn't anticipate the wetness that we did observe. The forecast actually resembles what we would tend to see during an El Nino event in which the southern tier of the United States sees above average probabilities of above average precipitation. And over the region of focus for at least this webinar today is that we had equal chances in terms of the forecast over the Missouri, Tennessee, Ohio, and Mississippi River basins. So really this forecast doesn't project too well onto what actually happened. So what are we doing here? So in this study, we set out to diagnose the causes and predictability of December to February 2019 U.S. precipitation. And given the forecast, we pose this as a question. Could America's wettest winter in 1819 have been anticipated? So the way we're going to do this here is our metric for U.S. winter precipitation is area average precipitation anomaly over the contiguous United States. We find here that the results are robust across different metrics. So an example of that is we used a metric that is based upon a coherence to the 1819 pattern, and we find very similar results. So we look at this through three lenses. The first one is through anthropogenic influences. The second is through the behaviors of sea surface temperatures and subseasonal to seasonal timescales, and then finally on initialized forecasts. I'll only focus here mostly on the anthropogenic influences, touch a little bit on the subseasonal to seasonal behaviors of sea surface temperatures, and I won't talk about initialized forecasts today. So beginning here with the anthropogenic effect, what we're doing here is to diagnose the anthropogenic effects using a hierarchy of Earth system model experiments. And these experiments are transient experiments, so they're free running in time. We've done a similar analysis with different methodologies, and if you're familiar with it, we've used a factual and counterfactual methodology and found some similar results. Here we're just going to present the transient because transient's a little bit easier to interpret. So what we do is we compare the anthropogenic effects by comparing two ensembles of transient experiments. The first is through a fully coupled Earth system model. It's a free-running model in which the radiative characteristics of the atmosphere and the aerosols are prescribed. The second is from an atmospheric model, and the same atmospheric model that is used in that fully coupled Earth system model. And it's a free-running model again, and it is based on using the same radiative characteristics and aerosols as the fully coupled Earth system model, but instead we specify the boundary conditions that were prescribed to observed estimates. And the two ensembles that we're using here are comprised both of 40 members. The first ensemble, that is the fully coupled model, is from the CESM large ensemble. And the second is the CAM5, which serves as the atmospheric model for CESM1. And if you're interested in seeing the simulations, downloading the simulations, we have them hosted here on our what we call our facility for climate assessments. So what we're doing here is to show the results from those transient model experiments, shown in terms of probability density functions for three discrete periods. In the blue is 1921 to 1940, in the green is 1961 to 1980, and in the red is 1901 to 2019. And what's key here is that the results from the two experiments differ quite a bit. On the left here is CESM1, the fully coupled model. And what we find is that anthropogenic influences increase the likelihoods of U.S. winters, as indicated by this shift in the distribution of precipitation during 2001 to 2019 relative to the two prior periods. This 0.59 corresponds to the value that we saw in 2018-19. And what we did is to find out what the relative risk of exceeding that number is within these model simulations. And what we find is that climate change within this model construct leads to a 1.8 times increase in precipitation exceeding that extreme value that we saw in 1819 relative to 1961 to 1980. Now on the right here is the CAM5, that's the atmospheric model. And the atmospheric model shows something rather different. And what we find is that a combination of the anthropogenic influences and the surface boundary conditions does not change the likelihood of U.S. winters in the same way as that fully coupled model. So for the same 20-year periods that we showed previously, we don't see that shift to wet conditions in subsequently later periods. Sorry about that, my computer's acting up. And so while the fully coupled model experiments suggesting that an increased likelihood of wet winters occurs because of climate change, that atmospheric model experiments forced by those same radiative characteristics does not. And what this indicates is that something else is a key contributing factor to these wet winters. Now what we do here is that we find that the change in extreme wet winter risk is related to tropical Pacific sea surface temperature anomaly patterns. So what I show here is the composite sea surface temperature anomaly patterns for CESM1 on the left, CAM5, and that is the observed conditions in the center panel, and on the right is the difference between the two. So for CESM, what we see is an SST anomaly expression that resembles El Nino. What I mean by that is greater warming over the central and eastern Pacific Ocean, relative to the central and the western Pacific Ocean. So this projects onto an El Nino pattern. And by contrast here, what we see is something rather different in the trace of observed sea surface temperatures between 2001 and 2019. And this is what CAM 5 was exposed to. We see a very warm West Pacific Ocean. We don't see too much in the way of warming over the central and eastern Pacific Ocean. And differencing the two, what comes out is really an El Nino-like pattern. So reconciling those differences between the CESM, that fully coupled model, and the atmospheric model as it relates to extreme wet winters is this El Nino pattern here. So an El Nino pattern, thereby increasing the odds of above average precipitation or extreme precipitation over the US. Now, going to the second point here. So these results that we see from the anthropogenic influences argument experiments, they motivate us to examine the effect of subseasonal to seasonal sea surface temperature extremes on US precipitation extremes. So that's what we're going to do here. What we do is we use atmospheric model ensembles, similar to the ones that we showed before. And we're going to diagnose two ensembles, CAM 5 that was previously used, and a second ensemble called the ECM 5 model. They're forced under the same boundary conditions. So what that means is the same sea surface temperatures for the time period of 1979 to the present are specified in the model, as are the radiative effects in the atmosphere due to a changing climate and also aerosols. And we compare the results from both of these experiments to make a diagnosis on how sea surface temperatures may play a role in affecting the risk of extreme wet winters. So in the last few moments, what I'll do here is to show that certain sea surface temperature configurations increase the risk of extreme wet winters. So extreme wet US winters are evaluated in the same way as before, as an area average over the contiguous United States. What I've done here is to change the threshold a little bit as to increase our sample size. So we're looking here at the top decile of precipitation within each model construct. So the figure on the left here is CAM 5, and the figure on the right here is ECM 5. And each of the three panels are the same in both figures. The top panel here are box plots of precipitation area averaged over the US, and then on top of that are dots that correspond to what we actually saw for precipitation during those seasons. The middle panel here is the change in the top decile risk during each season, and the bottom panel here is a measure of ocean conditions during that time from the Oceanic Nino Index. So what we get here is we find a couple of different things. The first one is that the sea surface temperature anomalies help to condition the risk of US precipitation extremes. So really noteworthy here and robust across both models is that the strong El Nino events of 1982-83, 98, and 2016 show up very well here. And by contrast, what we also see is these times during which we have a decreased risk of extreme US precipitation, they tend to also fall in line with La Niñas. But a little bit of a caveat here is they don't always fall in, so there's a little bit of nuance to the interpretation. Now for 2018-19, 2018-19 is interesting because there was no increase in the risk of extreme wet precipitation. We actually see a decrease in CAM 5 and no change in ECM 5. So in wrapping up here, what we did is we set out to diagnose the causes and predictability of the extreme US winter precipitation in 18-19. And we looked at this through three lenses: the anthropogenic influences and through the behaviors of sea surface temperature anomalies. That's it. Thank you.
Thanks so much, Andy. That was fantastic. And while we transition, there's a question: what is a free-running model? That's from Thomas Over.
Oh, well, it's a model where we just begin it from some initial condition. In the case of these models right here, they began in 1920, and then you just run the model out through whatever history that you're interested in. So we call them transient models in the sense that they just have free-running weather and climate through time.
Thanks very much. Our next speaker is Sarah Kapnick from NOAA OAR's Geophysical Fluid Dynamics Laboratory. She's the Deputy Division Leader and Research Physical Scientist. and seasonal to decadal variability and predictability division. Her research focuses on the mechanisms controlling the hydroclimate with an emphasis on precipitation, extreme storms, and mountain snowpack. Take it away, Sarah. Thank you for being here.
Thank you. So I am going to give the perspective of this from the couple modeling side, the global couple modeling side. So how do we study extreme water risks? My perspective from using the couple global models is that we can use them to generate sufficiently large data sets, so that's hundreds or thousands of years, ideally thousands of years, to explore extreme event probabilities. So why is this unique and why is this of use to us? So with the global climate models, by generating thousands of years of data, you can start to look at the really extreme tails of the distribution from the models directly in a way that you might not be able to estimate extremes from observations alone. So this is a plot from the lower Mississippi flood risk. On the left is a 100-year risk, so we don't have direct observations of the 100-year risk at certain locations along the Mississippi because we don't have 100 years of data. On the right-hand side, this is from Tabbert Landing, which has 87 years of data. And so you have a black dot for an estimate from the data of the 5-year risk of an extreme event of discharge in Mississippi. And so the black dot gives you the estimate from observations alone, but then the blue portion and the red, this is all coming from the model. And so from a model, if you have thousands of years of data, you can estimate the risk with all these, with all the different time series lengths. And so we can make estimates of what the risk is with each length of a GCM. So when you have roughly 100 years of data in the GCM as well in observations, you get an observational risk estimate of what the discharge is. And actually here, the observational estimate is less than that of the median of the GCM if you have the same amount of data. And then if you can't estimate actually the 100-year risk from observations alone. So what this shows is that with increasingly the length of a GCM record, you can reduce the estimate of what a risk is. So this all assumes that you believe the GCM is correct, but it allows us a way to estimate risks, particularly extreme tail risks. So to estimate extreme tests, you need a global climate modeling of sufficient resolution to be able to estimate the extreme of interest, and then you need thousands of years. You also need these things to be developed, and you also need available observations for comparison and validation. So the question that we are posed today is, how do you get inland flooding? So number one, you need the atmospheric forcing, you need precipitation of some sort. You have land surface processes, and then you can also have the built environments. You can have dams, you can have urban areas. So in the global climate modeling results that I'm going to show, we only have 1 and 2. So we only have the atmospheric forcing, or we have some land processes, but we're not including the built environment in this work. So first, I'm going to show you the climate perspective if you just have the atmospheric forcing. So what do we know from the climate modeling of extremes from precipitation alone? So all the work that I'm showing is from a postdoc that used to be in my division, Karen Vanderbilt has led, so this is U.S. extreme precipitations and how it scales with resolution. So in the upper left corner, you have observational data from CPC, 25-kilometer resolution. This is the magnitude of the annual daily extreme precipitation event in the United States. Then you have the different global climate models at increasing resolution. So you have the 200-kilometer model on the upper right, bottom left gives you the 50-kilometer model, and the bottom right gives you a 25-kilometer model. So as you increase resolution in the global climate models, you're able to increasingly be able to capture the magnitude of extreme precipitation as you do in the observational data. Also importantly, particularly when you start asking questions about risk during certain times of the year of certain extreme events, you have to ask, what is the seasonality of the precipitation extremes in our model as well? Do they coincide with the seasonality that you exhibit in reality. So interestingly, as you increase resolution, you also increase the proper seasonality of when the precipitation extremes is happening. So the upper left is again the observations, and then the upper right is the lowest resolution model. The interesting thing here is at 200-kilometer resolution, you somewhat resolve the Rockies. You don't really resolve the Appalachian Mountains or the Maritime Mountains. And so you see these distinct regions where you have certain seasonality relating to where the mountains are providing cutoff of moisture. And in the lowest resolution model, you can get the right precipitation extremes roughly of seasonality in the Missouri, but then when you go to other portions of the basins, because you don't have the mountains in the Appalachia, what's causing extreme precipitation is at the wrong timing, and it increasingly goes towards observations as you move to high resolutions. So the 50-kilometer model appears to be the minimum resolution to getting precipitation extremes roughly at the right time of year spatially, and it improves further as you go to higher resolution. So what if the models told us about changes in extreme precipitation risk? So this is from analysis of comparing a 1990 calculation of what extremes are versus double of CO2 from 1990 values. For here, I've chosen to look at the winter and the spring months for simplicity. So the increase in the mean daily precipitation values, so this is just the average, you have increases over much of the Mississippi Basin in December, but then it's really, or in the winter months, but then it's really increasing during the spring months. So how do precipitation extremes map onto this? When you look at the annual one-day extremes, the precipitation increases are actually even enhanced compared to what they were for the average. So the precipitation extremes are increasing at a percentage rate that is greater than what's happening in the mean. So we've used this analysis to try and understand how do you model precipitation extremes. We know that we can capture them in high resolution global climate models. We know that they're increasing in the winter and the spring. What does that mean for specific events? We've done some specific event analysis. This is from a case study that we did in the lower, in Louisiana for an extreme rainfall event that happened in 2016 in the summer. And from that, on the right-hand side, we were able to calculate from observations as well as from the models with hundreds of years of data, what is the change in likelihood of these extreme events from 1900 versus 2016? Again, what you see on this, this bar chart is the upper portions. The blue colors are both from observations. You have these wide ranges in what the characterization of the extremes might be, and that's due to the limited length of time series that you have from observations. And then when you move to the model results in the oranges and reds, you have much tighter bars. The bars are tightening up because we have more and more data, which allows us to decrease the spread and understanding what the changes in the extreme risks are and characterize them better. So from extreme rainfall, we're able to understand changes in extremes, and the models have been able to characterize them to understand precipitation extremes. However, as I said earlier, for inland flooding, it's not just precipitation extremes that lead to flooding events. And so we've started to look at our models to try and understand, can you characterize land surface flooding as well by including land processes? So in the GCMs, we actually do have Mississippi Basin with rivers in it, and this is what a river looks like in the GCM with the darker blue colors indicating increased flow. Again, this does not have the human management portion of water. There's no dams, there's no irrigation. There's no urban environment in this model. So we've looked at changes in discharge flows and different climate variables across the Mississippi Basin at that point at the lower Mississippi Basin in Louisiana before it hits the ocean. So this is the change in seasonality from 1861 to 1900 versus 2061 to 2100. And so across, you see you have increases in total basin precipitation, you have reductions in snowfall, and you have reductions in snowmelt except for in the winter months. The winter months, the snowmelt is expected to be the same in the past and the future from the model simulations that we've conducted. On a monthly basis, the changes in river discharge, so this is just an average basis, similarly expected to be the same roughly in the summer through winter, but then you have this divide in the spring. But the river discharge to the end of the Mississippi is expected to decline on average. But what does that mean for the extremes? So we created a control simulation in 1860 to try and look at all the extreme events in the model in February, March, and April. Interestingly, what causes an extreme in the model tends to actually be river discharge events coinciding with major snowmelt events. So it's the influx of water into the system coinciding at the same time that you then actually have increased river flows at the mouth of the basin. And this is, again, these are monthly values. These are not daily values. So what does that mean for the change, however? So we have a reduction actually in extreme snowmelt over time. We have an increase in extreme rainfall at the same time. What that means for river discharge extremes is actually river discharge extremes are seen to go down on average for the 1 year, the 5 year, and 20-year extremes, however, not for the 100-year extremes. In this case, we're not finding strong differences in the 100-year extremes, and more work is needed to understand the really extreme risks of changes in flood risks. And this is, again, for a point in the lower Mississippi. So from this work that we've done so far, we understand that GCMs can characterize the occurrence and change in extremes due to the ability to generate thousands of years of data, in particular for extreme precipitation. At higher resolutions in the global climate models, we can get the magnitude and seasonality of extremes. When we look at climate change signals, we see that they're expected to increase, particularly in the winter and the spring, particularly over the Mississippi Basin region. For river flows, we've done some initial work where we've looked at monthly flows. We've seen decreases in snowfall, increases in rainfall, similar to snowmelt in the winter months, but declines in the spring. And then put all together, monthly discharge extremes, so declining probabilities, but the 100-year risk is less uniform. So the really extreme events characterized by this point at the end of the Mississippi is less, it's not statistically significant of what the changes will be, so it requires more work to understand that, especially for the most extreme tail distribution of discharge. And so what are we doing to try and improve this? So these results that I was showing are from the GFDL floor model. We've had value in this approach over the last 15 years. It's very useful, but we're developing new modeling systems to be able to try and really look at extremes and characterize them, and do it on a seamless methodology from seasonal decadal prediction and projection, and for risk assessment. And for this future work of what we're developing is going to try and dig deeper into understanding those extremes and what characterizes them. And so Lena also will talk about the land surface model and what we do to improve that, to look at extremes on the land surface side. So with that, I can answer any questions.
Thanks very much, Sarah. There is a question. Adam Schlosser asks whether you've accounted for any of the river engineering in your estimates of century scale changes in extreme discharge. So for instance, the Mississippi is highly managed with a series of dams. And so how does that get factored into, or channelization, how do those get factored into those century scale estimates of extreme discharge?
Right, so those are not in the model. And I should have made this point when I said that in the middle of my talk, that we have to make a fundamental assumption that we can characterize extremes and monthly extremes because in discharge with the model without having that, by assuming that when the water is so extreme, the built environment with or without it, you will have extreme flooding in a natural climate sense without the managed river. with. But to be able to get at that question in the future, we will need models that are built that have some of that included.
Excellent. Well, and I'd also point out that on October 2nd, the webinar where we're going to be looking at anthropogenic, we're going to be looking at the societal impacts of this event, and we will be exploring that subject just a little bit more. One final question for you is, what's the name of the model you use to produce the discharges based on precipitation from the GCNs? And I'm going to transition talks while you answer that.
So the low resolution model is called LOR, the 50-kilometer one was called FLOR, and the high resolution one was called HIFLOR. And that was a 2016, I believe, Journal of Climate paper led by Karen Vanderwill, where you can find that information.
Thanks so much. Our next speaker is Gabriella Villarini. He's an associate professor in the Department of Civil and Environmental Engineering at the University of Iowa and the director of the IIHR Hydroscience and Engineering. His research broadly focuses on flood hydrology, extreme events, hydroclimatology, climate predictions and projections, and economic impacts of natural hazards. Thank you, Gabriella. Take it away.
Thank you very much. Thank you very much for having me here today. And I'm going to give you a little bit of an overview of some of the work we have been doing in relation to flooding, the frequency of flood events. And given that today's focus is on the 2019 Missouri Mississippi flood event, I'll focus my attention on the central United States. And I'll change gear a little bit from the previous talks and try to focus mostly on observations, historical records, and then try to look, see what we can learn from the observational record, and try to look forward in terms of projections. Before we jump into the 2019 event, I just want to highlight how the central US is an area that has been experiencing several large flood events. I'm going to show you a couple of photos here related to the 2008 flood event. The one on the left is the city of Iowa City, where the University of Iowa is. This is the Stanley Maxwell Hydraulics Laboratory, where I'm currently located. And in 2008, as I was finishing up my PhD work, we had to be evacuated from this building. This is in 2008, the city of Cedar Rapids. You see how large areas are completely underwater. And so the central US has been experiencing quite a few events. We heard 93, 2008, but also between 2008 and 2019, there have been several other events. But let's fast forward 11 years and let's look at the Missouri flood. We've seen some of these satellite images. This was the condition of the Missouri River on November 16th of 2018. The red lines are the levees, and you can see that the darker blue color is the water within the Missouri River. Fast forward March 16th, the Missouri definitely at a much higher stage. Levee breaches. You see on the eastern side, the east and west Nishnabotna rivers. Few days later, even more so, large areas of the western part of Iowa and eastern part of Nebraska completely underwater. And they remained underwater even longer as the water started to recede. And these had a number of implications from economic perspective, given the heavily agricultural economy that we have in this part of the country. As we go from the Missouri to the Mississippi, we can look at the situation, for instance, at the city of Davenport on the Mississippi River. This is a contrast between two situations, so basically 1 year apart. On the left, you have early May 2018. On the right, early May 2019. Much of the areas in 2018, much of the river was within the banks. Different situation in 2019 with the water affected the downtown areas in Davenport. Now, if we take an even broader perspective, these are for some of the locations where the U.S. Geological Survey has been collecting the data that also have threshold levels established by the National Weather Service for different levels of impacts between minor, moderate, and major flooding. You can see that large areas of the central U.S. were under at least minor flood level between March 1st and May 31st of 2019. Here, these orange colors. And how the moderate and major flooding were also affected several locations, in particular along the Mississippi and the Missouri River. You also see those blue color on the background, and what I'm showing you there are zip codes where there was at least one claim filed through the National Flood Insurance Program. And this is some work that I've been doing with, in particular, with Jed Sakowski, looking at the flood insurance issues associated with the 2019 Mississippi flood events. So, if we think, so one of the, based on the observational records, we have looked at the frequency of flooding across basically the second half of the 20th century into the first half of the 21st century. We've done the analysis across different seasons, and each season is within one of these rows, and we have examined the sensitivity of the results for different thresholds. As you move from left to right, the threshold is decreasing, and so what you're looking at is you go from less frequent to more frequent, kind of like nuisance flood events as you move to the from left to right. And across large areas of the central U.S., there has been an increase in the frequency of flood events, and this is consistent across thresholds and basically across season. Now, this is good. You know, we have looked at how things have changed in the past based on the observational record. The problem is, though, that what can we learn from just by looking at the historical records and saying that there are trends if we are still not completely sure as to what caused these trends. And so, just to give you an example, imagine you have identified that there are trends. What does it mean moving forward? Are you going to continue along the same trajectory? Are you going to start plateauing? Are you start going down? And so what we have been trying to do is to move away from a straightforward detection of changes into a more of a process understanding. Can we understand how we got to where we are? With the goal that if we understand how we got to where we are, we might be better positioned to say how things might be changing in the future, given the way that these drivers might be changing. And so I'm going to show you some results for 287 sites with the long-term record by USGS. These are sites that have at least 50 years of daily data covered in the second half of the 20th century and the first 2 decades of the 21st century. And even though we had the requirement of at least 50 years, most of the sites had much more than that. And what I want to focus on is the fact that we do this from a statistical perspective, and I'm definitely not going to wow you with some high-level complex statistical methods. The point here is, can we develop simple models where the changes from one year to the next can be described by processes or drivers that we know we expect to be related to changes in discharge and flooding. And so in particular, if you think about it, the central US is a highly agricultural part of the country, and so we would expect agriculture to play a role. We also have some big cities, and so in some locations we would expect urbanization to play a role. And so what we have done, and this is just a very simple example, for one location, we have computed the basin average agricultural intensity, basin average population density as a proxy for urbanization, basin average temperature, and basin average total precipitation. We've done this for every season. We have also computed what we refer to as antecedent wetness. And in a sense, the way we think of this antecedent wetness is a simple proxy that allows us to characterize the state of the basin before the season of interest. And so imagine you want to know, you want to model the frequency of flood events in the summer. The antecedent wetness would be the precipitation in the prior spring. And our response variable would be the number of events. Now we're dealing with a discrete variable. We use Poisson regression. And as I mentioned, this is some very simple modeling. We have between 2 and 4 parameters that we have to estimate at the most. And we don't tell what the right model, we don't decide a priori what the right model is, but in a sense, we let the data speak for themselves. And just to give you a sense for how well this model works, these models work, I'm showing you the results for a given site, 2 different thresholds, and results at the seasonal level. You see that the circles are the observations, basically what we're trying to represent. The white line, for instance, is the median of the Poisson distribution, and where the parameters of the Poisson distribution are coming from the values of the predictor for the given year. And so overall, these very simple models are able to capture very well the changes from one year to the next in the observational record across seasons and across thresholds. Now, this was one site. These are the results across the study domain. And again, from left to right, you go from less frequent to more frequent events, and from top to bottom, you go across different seasons. And overall, these very simple models, remember, we're estimating, we're describing the changes in the historical record using between the 2 and 4 parameters. These very simple models are able to characterize very well the changes in the observational records with correlation coefficient, values of correlation coefficient between 0.6, 0.7, 0.8. And so we have also evaluated this in the context of cross-validation. And so these are the results using all the data, but we obtained similar results through cross-validation. These simple models, they also allowed us to examine the relevance of different drivers. And so just to give you an example, if we are looking at the results in the left panels, at many of these locations, precipitation is the most important predictor. Now, as we lower the threshold and we're dealing with, let's say, less extreme or more common events, antecedent wetness becomes a more and more important driver, which suggests that as we would expect, in a sense, it was nice to be able to simply reconcile the fact that extreme events is the response to precipitation, that the storm rainfall that is very important. But as you go to more and more frequent flood events, it becomes antecedent wetness, or the soil saturation starts becoming more and more important. So now what we have are simple models where if you know what the future rainfall and temperature in particular are going to be, then you can say what the frequency of flood events might be expected to be. And we have done work at both at seasonal, decadal, and centennial timescales. But today I'm going to focus on the centennial scale. And in particular, what we've done, we've used the precipitation and temperature data from 2 data sets, the North American Cordex, NA Cordex, and the localized constructed analogs. The basic idea of both of these data sets is that they are downscaling from global climate models. And it's nice that the downscaling is performed using 2 different approaches. through the NA Cordex is dynamical downscaling, where the global climate models provide the boundary conditions for regional climate models. And for local, on the other hand, the downscaling is done in a statistical sense. They have higher resolution, as you would expect, compared to the original GCMs, and the NA Cordex has a 0.22 degree resolution, while 1/16 of a degree for LOCA. We consider both historical periods as well as the RCP 8.5. The first part of this study that we did looks at how well the statistical models fed with the historical runs by the GCMs, the NA Cordex and LOCA, it performs. And so the first part was for us to get a sense for the performance on the historical period. And once we were comfortable with it, then we used it for projections. What I'm showing you here on the left panels are the results based on LOCA, the right panels are the results based on the NA Cordex. And overall, over the course of the 21st century, the overall tendency are towards increasing trends, and this seems to be consistent across most of the seasons, across different thresholds, and for both of the data sets. Another thing that we actually did was then to look at a comparison between 3 different 30-year periods during the 21st century. And so you see them up here: 2006, 2035, 36, 69, and 1799, with respect to the historical period of 76 to 2005. So what we've done, we've compared the average number of flood events during these 30-year periods in the future with respect to the historical period. And we've done it again for LOCA and the Cordex. And the Cordex, these are the results for just one of the thresholds, but the results are consistent across the 4 different thresholds. And what we get is, as we would expect, as we go further, as we march through the 21st century, there is a stronger signal of average increase in frequency of flood events. And the signal tends to be more marked, the most significant during the spring season. And these results are consistent across both the LOCA and the NA Cordex. So just to wrap up, I have just a few key points. The first one is that there has been an increase in the frequency of flood events based on the observational records across the central US. We've been able to develop some very simple models that capture the year-to-year variability in this record, so doing a statistical attribution of these changes. We found that the largest projected changes are for the springtime, and that the signal becomes stronger as we move towards the end of the 21st century. And just to highlight some of the work we're currently doing, one is to look at, we have performed an attribution study of the 2019 Missouri-Mississippi flood events, and we've also been doing work trying to look not just at the attribution of the flood event, not just at the attribution of rainfall, not just at the attribution of the flood event, but also looking at an attribution to climate change of the economic impacts of flooding. And so with this, I'm going to stop and I'll take questions.
Thank you so much, Gabriella. In the interest of time and to finish on time, I'm going to move on to our last presentation. But of course, people are still welcome to post questions to the Q&A panel, and we will, as you suggest, be in touch with those questions in the near term. The anchor speaker for today is Elena Shiliakova. I'm sorry, Elena. We didn't meet to discuss the pronunciation of your name. She's a senior climate modeler at NOAA OAR's Geophysical Fluid Dynamics Laboratory and co-chair of the Land Model Division team. She focuses on the representation of land, hydrologic, and Earth system processes in climate models. Thank you for speaking today.
Hi, do you hear me?
Yes.
Hello? Okay, great. I just try to go fast over my slides because I don't want to miss any information because we're close to the end of the seminar. And GFDL doesn't have community in its name, in its land model, but it's truly a community of collaborators. And this group here, particularly, this presentation here is the outcome of hard work of my collaborators at USGS, Chris Mealy and Chris Tadan, my collaborators at GFDL, Sergei Malyshev, as well as our postdocs at Cooperative Institute, Eugene Zhang, and the former postdocs who are currently at Duke University, Nathaniel Cheney, and Dan Lee, who is now at Boston University. And I'm going to try to tell you not what we have done as much, but is where we're going, because I've been asked to talk about processes and improvements towards the inland flooding work, which could be done in the future very soon. Okay, first of all, land models we develop, they're global, but we try to capture heterogeneity of land at subgrid scale and represent not just natural systems, but also agricultural system, forestry, and different type of ecosystems, from forests to croplands to desert area. And because we're interested in developing this model for Earth system applications, these models can represent hydrological energy exchanges as well as biogeochemical interactions, including carbon. We're working on nitrogen, as well as the precursors of aerosols. And we try to capture processes which affect hydrological cycle efficiency and its components, which is why it's not on this picture. We also introduce urban systems. And we look at the components of hydrological cycles, such as transpiration, runoff, as well as modeling of water table, which is not the and soil moisture, which affect how much water actually in the system before it runs off. And these models could be applied at different spatial time scale, not just temporal time scales. We have run these models globally from 10-kilometer resolution to 200-kilometer resolution. And in our models at GFDL, the grid size on land is defined by what atmosphere chooses, but we could go below that resolution and represent subgrid heterogeneity for the system of tiles. This is sort of schematic of what the tiles could be. So let me just go briefly and say what's in GFDL LM4. LM4 is a new suite of models we developed during the last 5-7 years. Some of them are used, LM 4.0, for example, is used in SIM 4.0 and SPEAR model, which Sarah mentioned. LM 4.1, which has more sophisticated treatment of biogeochemical cycles and vegetation dynamics, and ASM 4.1. Also, we're working on a model we refer to as LM 4.2, which is suitable to subseasonal and seasonal predictions and has particular emphasis on representing hydrological processes. The land model is not a surface. A lot of people say land surface model. Our models are truly like three-dimensional land models, and they have depth, both above ground and below ground. We can represent soil and bedrock layers. We can have variably saturated water hydrolysis. We represent changes in soil temperature profiles, as well as processes of freeze and thaw. We have snow model, multi-layer snow model on top of the soil, and we could represent changes in the seasonal cycle and snow melt, which have been mentioned in previous representation, as well as groundwater table, including purge over the permafrost. The model captures permafrost. And then above ground processes, we have a whole suite of them, and some of them more relevant to the issues of inland flooding, including what is evapotranspiration and above the ground, including interception from trees, from transpiration through roots and from the soil evaporation. We have a river runoff network in the model, which collects runoff and snow melt from the surface and then, puts it through the whole network system all the way down to the ocean or lake. We have a water management now in development, and I'll touch briefly on that. We also have different type of vegetation and different type of manage and unmanaged ecosystems. And we do dynamic vegetation, plant phenology, and plant physiology. So, and all of those characteristics could be affected by land management, conversion, deforestation, conversion of agricultural land to urban areas, and vice versa. So there is a carbon and nitrogen cycles in the model, which could represent, for example, effects of increased water use efficiency, which could affect the transpiration, which could affect potentially runoff. There is also dust cycle and a water quality model. But the top of this list is probably more relevant to what we need to know. An example of the urban model we introduced in LM3, and now we integrating it into the LM4 suite, is the urban canyon model. Actually, it's 2 tiles, not one. We capture what happened on the roof and on the wall of the urban system, as well as what happened on the surface. And we represent surface as permeable and permeable surfaces, so we could simulate what is a runoff, let's say, from grassy areas within the cities, as well as from the paved areas in the cities. So the problem, with applying these urban models, that we have some idea about changes of the urban areas in time. And there are scenarios which are reconstructions available for us in the past and the future. The challenge in getting more realistic results is not just crudeness with which we capture the processes, but what is the specific characteristic of the permeable and permeable areas in the cities. Those data sets actually fairly broad stroke, and if we're interested in predicting particular area like Mississippi, for example, flooding, we would need to know, like, in more detail what's happening in the urban areas along those river corridors. So, and as I said before, the way we do river modeling at GFDL, we made a decision some time ago. Then we create new river network for every new atmospheric resolution. And it allows us to harmonize not just how river flows horizontally, but what are the exchanges between river and lake surfaces with atmosphere. Because as your resolution increases, amount of evaporation that will go into the atmosphere will depend on the surface of those water bodies. So every time we, for example, create this example on the left of a regional model, which is 1 to 3 kilometer resolution, we would have a much more resolved river network, which could be forced, let's say, from observed precipitation. Or if we go to the model like high flow, which Sarah mentioned before, we would create a 25-kilometer river network, and then we'll simulate not just how the water moves from left towards the ocean and lakes, but also what would be exchanges of evapotranspiration between rivers and the lakes and the surface. And on the right, this is example of changes in the stream flow in the future in idealized double CO2 experiments from present day. It's courtesy of Gabe Becker, who shared the slide with me. And you could see in blue tones everywhere where the stream flows increased, and in yellow the stream flows which have decreased. So we can we could look at what the changes in the water carried by the rivers in the past in the historical simulation, but also try to understand how it would change in the future. And as we change the resolution, we could go on higher and higher spatial scales to understand what might be the changes in flooding in the area. So all of those simulations were done with LM4 model. I think the right one is LM 3.0 and the left one LM 4.0. But we have the capabilities to capture the changes in stream flow as climate, precipitation, and many other forcing change in the system. So what we're doing now, we try to emphasize impact of the human water management. And we recently implemented our irrigation model into LM 4.0, I guess, right? And irrigation in GFDL models is prognostic. What it means that the model figures out how much extra water has to be added to the system, either from the rivers, reservoirs, or from the groundwater. And Chris Mealy and Eugene Zhang led that development. And it's interesting that their first results suggest that irrigation has a teleconnection effect on the precipitation in some other regions. So it's not simply like how much water you add, but irrigation itself has a potential to affect precipitation in other global regions worldwide. So hopefully, they submitted a paper and we could share results with you very soon. And another unique feature, I think, of GFDL model, we represent, like Eugene and Chris, in collaboration with other scientists, represented time-varying reservoirs in the systems. So we have a lake, two types of lakes, natural lakes and lake, which we call reservoirs. And locations of them known worldwide. This is a data set which USGS and Chris Miller shared with us, and they actually change in time. There's a history of this reservoirs recorded and available for the modelers. So, and because reservoirs are used as sources for irrigation, they're used actually as a methods to do flood control. They use for hydropower, and they also use for river navigation. We think it's important features which need to be understood and fully integrated in the future projections of land flooding. And this is also already operational. And again, like Eugene is preparing the analysis of this work. So, and the next thing I want to touch briefly is it's not just the amount of water which affects flooding, but also the shape of the landscape. And as you know, the features, the heterogeneity of landscape occurs at the 10 to 100 meter scale, and GFDL models or any other climate models barely can go below 10 kilometers right now for climate simulation. So important question emerges, like how do you represent events like flooding, which occur on a small scale, in these computational models which are not designed explicitly to represent hydrological cycle at those scales and only can afford 10 to 50 kilometer resolution. So one of our former postdocs, Nate Cheney, who is now a faculty at Duke University, developed this pioneering approach. What we do essentially, we try to figure out how do you actually present first heterogeneity in landscape in the model. And you cannot put every 30 meters like
Elena, we seem to have lost your audio feed. Are you there? If someone could, if other folks could put in the chat if they've lost Elena's audio feed, I will attempt to reach back out to her. Okay, I will attempt to remedy this. If everyone please stand by.
Subdivided into hello?
Oh, Elena, you just you were gone for about 30 seconds. So
Okay.
the last thing I heard was about you can't incorporate 30 meter resolution data.
Okay, you cannot incorporate 30 meters data directly into 10 kilometer grid or 25 kilometer grid. So one needs to pre-process the data and figure out how to do it statistically without losing computational feasibility. So Nate Cheney and our collaborators at GFDL come up with the method based on machine learning how to do it. So, and we have implemented the model we call LM 4.2 using this Hydra block approach, which can go back and forth and essentially get the simulation which capture all that data richness, but at the same time go back to each of those 30-meter tiles and say what would be their characteristics, for example, runoff, soil moisture, given a much smaller number of the tiles in the model. So the point is here, you could go back and forth between the scales, and machine learning translators allow us to do it. And we could develop this type, we're developing these subgrid tiling methods for different atmospheric resolutions we're using. And furthermore, one more thing we do, which is very innovative, is that we don't think the grid, the land grid, is flat. Our GFDL land grid is actually tilted. And then we slice them like a loaf and bread into the pieces, and we compute all the soil characteristics, all runoff characteristics based on what's happening in each of those subgrid tiles. And the water flows two ways. It goes down because of gravity, and it grows along those tiles because of hill slopes. And some tiles end up being flooded. That's how we simulate wetlands. And other tiles, upland tiles, they dry because it's just water doesn't stay there, because we know water goes downhill. So, and this type of models are now being coupled to atmospheric models. We have run simulation in CM4 just to test it. And now we bring in that type of capability in the next generation of the GFDL climate models. But one more thing remains. Now we could scale vegetation, we could scale soil types, we could scale some of the geomorphological features. One of the hardest things to do is to scale streams. And this is something that's what is currently at the heart of our research. Nate and his collaborators developing further refinement of the styling hydroblock approach, where we're not just scale like physical, like a vertical structures of the land, we're also scaling how the stream network of stream is working. So, and I think it's something that will require coordination and collaboration with many people on this call and other possible collaborators, as well as the resources to support this type of research, which has never been done, but we think it's doable, and I think we have methods to do it. And hopefully, this would be a partner, I would say, to the work which is done with statistical model to use process-based approaches to predict inland flooding, both on the current climate and the future climate. And we see that as a cutting edge in that type of research. So, in summary, LM4 developments focus on improving hydrological, physical, and ecological process representation, central to improving inland flooding. But also, we need to develop novel methods to translate across scales different type of heterogeneity by utilizing the wealth of the data we have and using machine learning approaches to make them tractable and computationally feasible, even with all the resources we have. Thank you.
Thank you so much, Elena. And given that we did lose the audio for a moment, we'll just take one question. Bryce Anderson asks about the slide that you showed of the Amazon basin. He wanted clarification about the main channel there drying out, whereas the coastal watersheds seem to be, well, it looks like the Orinoco River also wetter. So could you comment a bit on that?
Well, in this simulation, and Sarah could also chime in on this, my understanding that high flow was run under current climate and under 2CO2. And as you change the climate, it changes circulation patterns, which affect precipitation, but also you change how much water precipitation you have in the air. So I would, my understanding is some of it is due to both changes in precipitation, but in high latitudes, I think it changes both in the temperature regimes. But if you look at Amazon specifically, I would think that, you know, it's a combination of changes in precipitation and intensity and some circulation changes as well. I don't know if Sarah wants to add.
Thanks very much. And that concludes our time today. It's been a very stimulating 90 minutes. We've covered observations and models and some of the future of modeling even. So it's really gratifying to hear from all of you panelists. So thank you very much. I know I represent the audience and my appreciation. And we will be back online on October 2nd for another webinar in which we discuss the socioeconomic impacts of this flooding event from 2019. And hopefully this is part of the longer-term conversation that the Climate Program Office participates in. We'll send follow-ups to answers if you haven't received them, and everybody have a wonderful day.